Hey guys, today we're going to do logarithmic functions, which is section 4.2 in your book. So what is a logarithmic function? It goes hand in hand with exponents. So log form actually has an equivalent exponent form. Now, to me, exponent form makes a lot more sense than log form. So the first thing that we're going to do is we're going to switch from log form into exponent form, exponential form. So it's always your base right here, log base 7 of x. Your base is 7. So we say 7. Oh, maybe not. Let's try that again. We say 7 to the power of 3 equals x. And that's how you put it in exponential form. Now this makes more sense to me, 7 cubed. Right? X is whatever 7 cubed is. Here, b to the power of 2 equals 25. And again, I can look at that now and say, oh, b is 5, right? 5 squared is 25, or negative 5. But again, it makes a lot more sense in that exponential form. Here, 4 to the power of y, 4 to the power of y equals 26. So this is just changing it into exponential form, to be honest, where it makes more sense. You could also take from exponential form and put it back into log form. So here's how I always do it. I say log base 2 to the power of 5 equals x. Because again, that's how you would have read it. 2 to the power of 5 equals x. Even if I think in the software, like it switches these, it writes it this way. It's the same thing. It's the same exact thing, so it doesn't matter which side the 5's on. Here, so again, b to the power of 3 equals 27. E to the power of y equals 33. E to the power of y equals 33. So again, just double check and make sure that you put them in the right places. You can also evaluate them by putting them in that exponential form. So this is saying 10 to some power equals 100. All right? So 10 to what power? 10 squared. So log base 10 of 100 is 2, because 10 squared gets me 100. Here, 5 to some power gets me 1 over 125. Well, we know 5 cubed is 125, so 5 to the negative 3 is 1 over 125. Again, 36 to what power gets me 6. So here we know we need to take a square root. Remember, square root is 1 over 2, right? Power over root. We want to raise it to the 1/2 power. 36 to the 1/2 power is the square root of 36. So 36 to the 1/2 power is 6. Here, 3 to some power is the 7th root of 3. This one's a little bit harder. If it makes you feel better to put this into exponential form instead of radical, remember it's power over root, so it's the first power, and we want the 7th root. A lot easier to see here. X is 1/7. That's telling us to take a 7th root, power over root. All right, so you can use these to evaluate. You can use them to evaluate, putting it in exponential form. Now, these are properties that they wanted me to kind of like list out for you, but I feel like you can use your head and I don't need to give you more properties. 9 to some power gets me 9. Well, we know it's 1. And it's a property, it's always going to happen. Here, 8 to some power gets me 1. Well, what do I have to raise 8 to? I have to raise it to the 0 power. So they just wanted you to see those because they do show up quite a bit and they're pretty easy. Here, the inverse property of logs. So here, b to the x equals b to the x. So when you start seeing these, you say 7 to some power, right, equals 7 to the 8th. Well, you know x is 8. So it winds up being that value of x, and that's what they're trying to show you here. Same concept here. It winds up being that value of x, but why? Write this back in log form. Write this back in log form. So what do we have? Log. So we have log 3 to the power of log base. That's bad. We're going to erase that. Log base 3 of 17, and we want to know, so we have 3 to that power equals something. We want to know what it equals. Well, when you look here, notice x has to be 17. So it winds up being that little number on the end. Same concept here, and that's what this is trying to show you. So even if you forget this, you can still kind of work it out. Graphing. So logs and exponents go hand in hand. So we did exponents yesterday, and we're going to start there today. So we have x, y coordinates. How about we do 0, -1, -2? I know we did this a lot yesterday. 3 to the 0 power is 1. 3 to the first, 3 to the second, and then the -1 is 1. Oops. I'm losing it here. There we go. Is 1/3. And to the -2 is 1/9. And we graphed yesterday. 1, 3, 2, 9. And remember our horizontal asymptote. Oh. Should get, this is really crooked, I'm sorry guys. But you should get really, really close to that horizontal asymptote of y equals 0, but never cross it. And you should definitely not be wiggly here like I am. So that's my 3 to the power of x. Now the log, remember we talked about inverse. We talked about inverse functions. The log is the inverse. So exponents and logs go hand in hand. So remember when we talked about inverse functions, I think that was on Monday, we switched the coordinates. So this was 0, 1, now it's going to be 1, 0. This was 1, 3, now it's going to be 3, 1. This was 2, 9, now it's going to be 9, 2. Right? And then again, we're getting really, really close. So this one's going to keep going up exponentially. And this is going to get really, really close to 0, but never hit. So this one we actually have, so here we had a horizontal asymptote, right? Our horizontal asymptote was y equals 0. Here, for our log function, we're actually going to have a vertical asymptote, of x equals 0, right? That line going up and down. So yeah, understand the asymptotes and how we're going to get really, really close but never cross, and understand how those functions go together, right? They are inverses, which is why we started our week with inverses. Everything still applies, okay? If it's with the x, that's moving you left and right. Think opposite of what you would normally think. You have stretches and compressions if there's a number out front. Reflections if you have a negative, and then you have your vertical translation if it's just on the end, right? Up and down. Domain. So the domain of log base b of g of x, so log base b of something, consists of all x for which g of x is greater than 0. So if you're trying to find the domain, we need x minus 5 to be greater than 0. So we need x to be greater than 5. So if we're writing that in interval notation, we need x to be greater than 5, so we want 5 to infinity. and we cannot include 5. So they both get parentheses. This one is a word problem, and you're actually going to, so log base 10, they actually just stop writing the base. So if you ever see like log of 100, they're trying to tell you it's log base 10 of 100. On your calculator, the log button on your calculator, it is in base 10. So anything you type in there has to be base 10, which is what this is. So notice there's no base down here. It's an assumed base of 10. So we've got 29 plus 48.8, and then log of x plus 1. So what's our x? X represents the boy's age. So the boy's age was 10. 10 plus 1 is 11. And you would actually go type this in. You'd say 29 plus 48.8. You'd hit the log button. Again, it says assumed base 10, and you'd say 11. All right. And when you type that in your calculator, you should get 80%-ish. All right, so what percentage of adult height is attained by age 10? About 80% of your adult height is attained by age 10. So you're almost done growing by age 10. Magnitude on a Richter scale. So this is talking about the Richter scale. The magnitude of an earthquake is given by the intensity is given by this formula, where I sub 0 is the intensity of a barely felt 0 level earthquake. So this is 0 level. The earthquake that destroyed San Francisco in 1906 was 10 to the 8.3 power times as intense. So the intensity was 10 to the 8.3 times the initial, or sorry, the intensity of a barely felt 0 level earthquake. So we're here. If we want to find out where we're at on the Richter scale, we do log. Again, instead of I, we're going to say it was 10 to the 8.3 times whatever 0 level was. And the bottom, we still have 0 level. So those are going to cancel. And what we need to type into our calculator is log of 10 to the 8.3. To be honest, you really don't even need to type it into your calculator. Remember, this is base 10, right? If there's no base, it's a base 10. So you're saying 10 to some power is 10 to the 8.3. So your answer is 8.3. All right, if you need me to write it, 10 to some power is 10 to the 8.3. That's what that's saying. 10 to some power is 10 to the 8.3. All right, moving on. Same concept as before with domain. So we need 4 minus x to be greater than 0. Natural log is a base of e. So an assumed base of e here. So we got negative x has to be greater than 4, negative 4, sorry. Divide by negative 1, make sure that sign flips. So we have x has to be less than 4. So we have negative infinity to 4, and none of them are included. Here, x squared has to be greater than 0. Understand this is positive and negative because negative 2 squared is greater than 0. So we want negative infinity to 0 and 0 to infinity. So we just want to exclude 0. And then this last one, sorry, I'm trying to speed up to beat this clock. Here we're using this function. They want to know after 50 minutes what happens. And again, there should be an ln key. Just like there was a log key, there should be a natural log key. So in your calculator, you do 13.4. You hit that natural log, ln, 50. Close that parenthesis, and then do minus 11.6. And you should get 41 degrees. And they ask you how well does the function model the actual increase. So after 50 minutes, it went up 41 degrees. So actually it models it really well. All right, bye guys.